A really advanced Python, and I came 2 years ago and listened to what people said, and I'm not going to talk about a fancy package like we've been hearing the last couple of days. I'm just going to say, how can I use these tools to solve some of the problems that I want to solve? And I like to work from concrete to more abstract. Well, we've been hearing a lot of very abstract things. And so that was where I was coming from on this. And after working with these, I thought that I'd share some of my experience. And so my personal motivation was to, so I'm going to use this outline of the presentation. I'm going to talk a little bit more about my personal motivation, and then I'm going to talk about this algorithm that was written up in a paper where Spitz describes a synthetic and a process to apply. And then I'm going to go and demonstrate go into an IPython notebook and show you some of the implementation. And then wrap it up with some conclusions and questions and answers. There is a long paper online. If you go to my abstract, you should be able to click to it, and it describes, has a lot of code and words that describe in detail what I was doing. So, as I've indicated, I do seismic work. I do signal processing in this case. I've done some migration in the past. But I'm really a Python beginner. And so in order to develop my Python skills, I wanted to be able to work and understand the tools that I'm used to using for signal processing. Things like Fourier analysis, linear algebra, filter and convolution, and showing the results in with Matplotlib. And so in order to develop those skills, I was practicing with the Spitz Prony algorithm. And just to be concrete about this, is I started with the nthought canopy program and the IPython notebook, and I created some prototypes that I hope to be able to use this as a template if I want to experiment with another algorithm. So if you read Spitz's paper, it's from 1999, he talks about a particular synthetic. And the event that we're looking at here, this consists of two events that he summed together. Both of them appear at 200 milliseconds. One of them is constant amplitude, and the other has amplitude that exponentially increases by 5% each trace. And the objective of his exercise is to break it into two pieces to try to separate this exponentially increasing event from the other one, and then to take a model of noise, this event. You said from another place you get another estimate of what should the noise look like, and then try to decide which of the components are the noise so that you can throw it away, and which component is a signal that you want to keep. And so I want to, this just kind of summarizes a lot of the words that I just said, but I'm going to build this exponentially increasing event with simple spikes and then band limit them in the frequency domain. And to band limit, I'm going to use the NumPy FFT, real FFT and inverse real FFT. And for the coherent model, I created that just by applying a negative derivative filter to the traces. And then when you split the objectives, these figures are just copied straight out of Spitz's paper. He says, see, this is my synthetic, and he describes it. And see, after I decompose it, these are the two components that I get out, and one of them has constant amplitude, and it looks a lot like the model of the noise I had, and so that's the one I'm going to throw away, and this is my signal. And he has a long paragraph, and you can read through this if you wish to, but the point is that there's just a lot of words. And really, this looks just like when I started working in industry, we had a guy we called a research geophysicist, and he had a number 2 pencil on a piece of paper, and he wrote all this stuff, and he gave it to a guy that we called a programmer that went and coded all this stuff up, and he said, take these number in this array and do this to it, and when you get done with the code, run this piece of synthetic data. And this is what this looks like, and you should get answers that look just like this. And I took it as a challenge to write this program like he did, and if you get the same answers, then you know what he did. And he explains in a lot of detail, but sometimes he uses some funny words that don't make a whole lot of sense, that are not standard technical jargon. Things like pattern. It sounds like that's not a word that really means anything that's in the title. The algorithm. I'm going to go step by step. If you want to know more about the theory, it's all in Marple, and he describes what prony is. Spitz never calls it prony, but the technique is that. And so the flow that we're going to go through is to Fourier transform the data, a 2D array of numbers transformed the one axis from time to frequency, and then loop over each frequency, and I compute a 2-point prediction error filter, and then a 3-point prediction error filter, and then he says deconvolve the 3-point filter with the 2-point filter, which is words for recursive filtering, is what would be called in the documentation of the routines that I use in the SciPy linear filter, L filter. And then you have these two time series, and you compute what he calls the pattern, which is computed by recursive, using one of these prediction error filters as a recursive filter to apply to an impulse, a 1 followed by a bunch of zeros. Once you get those, then you say, my data should be a linear combination of those two things. So the program has to address a number of the key routines that we use in geophysics, like convolution, Fourier transforms. And let's see what I've got next. So at this stage, I'm going to go ahead and move on to the IPython notebook and show you some of the code that I use to develop that. So if I can. So what I've done here is to, in the notebook, I tell it to make my matplotlib diagrams inline, and then I import the libraries that I'm interested in, NumPy, SciPy, the SciPy signal, and then the matplotlib. And the first thing I had to do is I defined a radix 2. FFTs run much faster if you ask for the length of the FFT to be a product of powers of 2, 3, and 5. I don't know why there's not a mixed radix FFT, or mixed radix computation, next radix, where you just say, give me a number that is a product of 2s, 3s, and 5s that are a little bit bigger than this, and so I wrote one of my own. Somebody might tell me later on that I didn't look in the right place. The next thing I'm going to do is, after I FFT the data, I'm going to ramp it, and so I need to be able to, I want a simple ramp that goes, that is at 1 at the low frequencies, up to 40% in Nyquist, and then it goes to 0 at 60% in Nyquist and on to Nyquist. And so that computation can be done at this point here, where I'm using some, where I set the low frequency. This is frequency slicing here, where I say from index 0 to ramp start, set those amplitudes to 1. And from indexes ramp start through ramp length, I use this lens space that starts at 1 and goes down to 0. And then above that value, I want to set those to 0. And then I check to make sure I'm doing the right thing with a plot, and this is the graph that I obtained from that. And so I say, okay, good. When I get my Fourier domain, then I can multiply it by that. And then in the description of the model, it says I want a spike at 200 milliseconds that's constant, and I want a spike at 200 milliseconds that increases with space 5% per trace. And so I'm going to band limit, and so this is how I've done that. I first set up an array of zeros, and then this is array slicing in NumPy, which says take sample number 51 for all x locations and replace it with this array here, which says it's 1.05 to the power increase, where it's 0, 1, 2, 3 from this lens space. And the noise is very similar. It's even simpler, where it's just a constant amplitude. Now there are FFTs in SciPy and in NumPy. The ones in, I was unable to get the ones in, I didn't have success with the ones in SciPy and was told to use the ones in NumPy. And so I've done that here. And this says, it looks like I've modified this cell a little bit so I won't be able to run it again. So I FFT the data, take it from the, this should say S equals the Fourier dual, which in capital S is computed off of the space domain S by taking a real Fourier transform, and then I ramp it simply by multiplying it by the S is multiplied by the ramp. So it's very easy to do these with array slicing and NumPy computations that allowed me to do this very quickly. The noise that was in there was also band limited, constant amplitude, that time sequences Fourier transform ramped and then inverse Fourier transformed. And then the final data is created by summing together in either the frequency, in both the frequency and in the space domain, or in the wave number and in the space domain, summing together those arrays. And then I view the three results. Here's the exponentially increasing, this is the constant, and this is the sum of the two. This is the data set you wish to decompose back into the original two pieces. And the model of the noise is done by applying the negative derivative filter using the L filter, the routine in SciPy signal. I used that one instead of the one in NumPy because I wanted to have both later I want to have a recursive filter. This is the filter, convolutional filter, which is in the numerator if you think Z transforms. This is the recursive filter, a simple impulse, which is in the denominator. And you apply it to this time series, and it creates this time series, which I take into the Fourier domain. And it creates this signal here, the one with the derivative. The next stage in the process calls for prediction filtering. It says a sample on the time series can be computed from the previous sample. This point is computed from the previous point by multiplying it by a complex number. And you want to know what complex number, when I apply it to each of these points here, will give me these points. Very simple one-point filter that's being applied. It's just it's not even really a filter, but it's a degenerative filter. And so you can set these up. These time-shifted filters can be set up using the array slicing. So you see here I've taken the points 0 through 1 to the end, and I've put it into this array. And the way that you solve one of these problems is you're going to multiply both sides by the transpose of the array over here. And so I multiply both sides by the conjugate transpose. And then I solve the answer. This is the matrix. This is the right-hand side. And it is a symmetric positive definite, and so I ask for that true. And that gives me the filter, the prediction filter, and the prediction error filter is just computed by putting a 1 in front of the negative of the filter. And in the description of the paper, it says when you do this, you should get the filter that looks like 1 minus 1, and indeed, when I ran it, I got those values out, indicating that I'm on track. So this the specification written by Spitz follows step by step. Now, that was a trivial filter. This is a little bit more two-point filter. It's more complicated. It's really a matrix instead of just a vector. Computed in almost the same way to get the filter, the three-point filter that he requires, which produces the same results as the paper. And finally, he says to apply recursively filter the two-point filter, FB, with or the three-point filter with the two-point filter, and you get a second one. And it indeed is the numbers that he provided. So step by step, he follows the description, and then he says the patterns, which I understood to be the pattern, which is his terminology for the taking an impulse and recursively filtering it with these prediction error filters. The objective is to compute that, fit the original data with these two reciprocal coefficients. And so the 1 over pf A is applied by taking an impulse response and filtering it with the prediction error filter. I'm sorry, this is the denominator, and I think this is the numerator of the filter. This is the denominator, the recursive filter, and this is the impulse response, the 1 followed by a bunch of zeros to produce 1 over pf A, and 1 over pf C is computed in a very similar way. And once you have these two filters, you can then ask to fit these two filters to your data. And so here I'm doing that simple regression that says what is the best linear combination of these two filters, the best of these two vectors, 1 over pf A and 1 over pf C, that most closely fits my data. So here I set up the matrix, multiply it by the conjugate transpose, and try to set it equal to the right-hand side. So here I solve it using the linear algebra solve. So, and when I did that, I did indeed get these exponential increase in constant amplitude results that I should expect. So I proceeded to find a function, and once I had the function, I could loop over it and do it at every frequency. And when I did that, I got indeed this decomposition. So that was the adventure that I went on, and hope that by sharing. Yes, sir. Okay. Pretty good time to wrap up then. So I was able to use these various tools, and I hope by sharing it with you, the short list of functions that I found useful within NumPy and SciPy, that you'll benefit from my experience. So this is just to wrap up conclusion, where I passed you through my personal motivation, the synthetic and process that I reproduce using the IPython notebook and the key functions, and I'm ready to take any questions if you'd like to follow, if you'd like to ask anything.